Hi, my name is Diablo and I wanted to preface this video with the following message. I have been working on this circuit network video for a very long time. Unfortunately, it would seem too long as 0.15 hit this week and made most of the information in this video obsolete. If you are here with a 0.15 build somewhere in the future and looking for circuit network information, then I'm sorry, but all the information in this video is only relevant for the 0.14 build. However, I did not want to throw all this work away. I did not want to, have it all be for nothing. So I will upload it and make sure that at least the parts that I had finished are accessible to the public. I do apologize for not getting it done in time. I do apologize for not getting it done at all. I'm not sure if I'm going to start this entire project over again for 0.15. I might, but I would have to have some time to think about that and to get my energy back. So without further ado, please enjoy Circuit Networks for 0.14. Welcome to Explaining Factorio, a show where I explain certain aspects of the game Factorio. My name is Diablo, and this episode we shall talk about circuit networks. First off, I have to say this took me a lot longer and was a lot more work than I had initially anticipated. There's so much depth and complexity with this system that it took me a while to get everything clear and in the right order so that I could actually make some sense of what was going on. As usual, the same caveat still applies. I may forget something, I may even get things wrong. If you find this has happened, please leave a comment down below in a calm and constructive manner, so we can all learn from this, and I will try to respond to them as best I can if needed. Also, the circuit network allows for extremely complex behavior to exist in the game. I'll be showing some simple examples of what can be done, but in the end it's up to you to combine the different components that I will be discussing here today. I am not a mathematician, I am not a programmer, so the complexity of the systems you are building is purely up to your imagination and your creativity. As I said, I will be showing some simple examples throughout this episode of what is possible. I'll put timestamps into the description so you can jump to any section that you are interested in. The circuit network. The circuit network is a closed network containing information only available within that network, meaning that only entities that are directly connected by either a red or a green wire are part of the same circuit network. This in contrast to the logistics system, where there is a certain global awareness of certain information. For instance, if I take this arm, connect it like that, and then take a wire and connect it to that box, this is now a closed circuit network, or circuit network for short. If I take another arm and connect that with also a red wire to that box, now this circuit network is not aware of this circuit network. How do I know that? Because if I check this arm, this inserter, it says connected to network 366. If I, however, look at this inserter, it says connected to network 367. So they are separate networks and the information contained within them are separated. Of course, if I now connect this inserter to this box, that will change the uh, existing network that was there, there's 367, back one number to 366 because that was an earlier existing network. So now they are one network. Just a little caveat here, just to let you know a little bit of information. You cannot remove a single wire. So now this inserter is connected to that box and it is connected to that box. If I only wanted to remove this wire, that's not possible. I can remove the entire apparatus and then replace it and put the wire in again, but I cannot remove the wire from this inserter. That's not a thing that is done. The same goes for power poles. If you want to remove wires from power poles, you can shift click them, but that will remove all wires. You cannot remove just one wire. Circuit networks in itself are not a very complex thing, as you can see. I mean, this is just an arm and it has a box attached to it, and we can say, well, enable or disable depending on what the circuit network says. Let's say if there is, I don't know, wood in the box. If you detect wood, if your input signal is wood, and we know that the box only outputs a signal, and it's bigger than 0, start working. It is not, so therefore it isn't. We can also say if it's equal to 0, then start working, because this always means start working. So now there is no wood in the system, meaning that wood equals 0. So you can see the light here has turned green, meaning that it will start working. Of course, if I then say bigger than 0, which it is not because it is 0, it will stop working, light is turned to red, and same goes for smaller than 0. Light is turned to red. So as you can see, circuit networks in itself are not a very complex thing. They are, however, capable of becoming as complex as your imagination will allow. What I mean by that is that you can basically accomplish almost anything you can think of in the game through circuit networks. And that is not even mentioning the infinite possibilities that mods bring to this game. We've seen some incredible feats of engineering already, with entire music video clips being played in-engine. With that being said, I'm not here to show every possible contraption that you can build. There are lots of excellent videos and posts and blueprints out there already. What I'll be focusing on today is how the basics of the system work and what to keep in mind when setting up your circuit network. The basics. So what are the basics of the circuit network system? There are a few things you will need to know to build that awesome idea you had. Here is a quick overview. Red and green wire hold separate information. Multiple sources of information on the same wire will be added together. The UPS value is used by entities to update their status. And lastly, combinators, combinators, combinators. So the first thing I mentioned was that red and green wire hold separate information. This allows you to run different sets of information along the same power poles from one area to the next. It also allows for 2 types of input and 2 types of output per combinator. Although you can have different values on the input, the output of a combinator will always have the same value for both red and green wire. The second thing was multiple sources of information on the same wire will be added together. This means that if you have 2 red wires that connect to the same point, the information on those wires will be added as a whole and also as separate entity information. For example, we have two red wires with information. The first with a count of 20 wood and 50 stone, and the second with 100 wood. The combined information will be 120 wood, 50 stone, and 170 total items. Now, to make this a little bit more complex, if the first wire had a negative 20 wood instead of a positive 20 wood, the combined information would be 80 wood, 50 stone, and 130 total items. Now, UPS. UPS stands for updates per second. Factorio will always try to run at 60 UPS. In other words, for every 60 ticks or updates of the game, 1 second of real time should have passed. Don't confuse FPS or frames per second with UPS. In theory, you can have 10 FPS, but the game could still be calculating updates at 60 UPS. For example, here is a screenshot that I took of my beltless mega factory, which at the time was running about 50 FPS, but was still being calculated at around 60 UPS. Every entity in the game has a certain number of milliseconds for its information to be updated. The total number of milliseconds per tick for a 60 UPS game is just over 16. We can easily calculate this by dividing 1000 milliseconds, or 1 second, by 60 updates, giving us 16.6 milliseconds per update. Most of this time is used by the vanilla entities in the game, so adding mods can impact your UPS significantly, especially in higher quantities. What does all that mean? Well, if your game runs at 30 UPS, then effectively your game is running at half speed, meaning all actions and calculations will take twice as long. For circuit networks, however, we can use UPS to set up some very intricate systems. Some entities, like the inserter and the belt, for instance, can update their information per tick, so these will be greatly affected by a drop in UPS. Now, the last thing I mentioned was combinators. So let's have a look at those. Combinators. Combinators are the backbone to any complex system. They are somewhat comparable to a microchip or programming language. Of course, in a microchip there would be millions of these combinators all packed together to perform a task, and every line of code in a program could be viewed as a combinator, where many lines of code work together to perform a task. Now, there are three types of combinators: the constant, the decider, and the arithmetic. But what's the difference? The constant combinator. The constant combinator can send out a permanent signal into the circuit network. It does nothing to change that signal or adjust it in any way. It is precisely as the name implies, a constant signal that does not change, unless of course you change it manually. Now, this can be very useful if, for instance, you want to tell the system that it can build no more than a set amount of items, and that when this amount is reached, the assemblers should stop producing. The decider combinator. The decider combinator is a relatively simple combinator which checks whether value 1 is either bigger than, smaller than, or equal to value 2, and then outputs a signal based on whether the result is true or false. When the comparison is false, no output signal is generated. However, there are two possible output signals when the comparison is true. The first is a specified output signal with a value of 1. If you do not set an output signal, no output will be generated. The second will output a copy of the amount of a specified input signal. For instance, if the input signal is 50 stone, I can have the output signal also be 50 stone. If you set this condition with an output signal that does not match the input signal, no output signal will be generated. This could be useful if you only wanted to output a certain signal if other criteria were met first. Like I said with the constant combinator, it can be very useful to control the amount of items being produced from an assembler. Here I have an example of the two combinators working together to restrict production for this assembler. Now, what can we see? We can see that we have a constant combinator here and a decider combinator over here. Now, the constant combinator is outputting a signal A with a value of 10. The other signal coming into the decider combinator is whatever's in this box. At the moment there's nothing in this box, but when this assembler will start producing gear wheels, it will output them to this box, so one of the signals then becomes gear wheels. Now, there's a very simple calculation going on, saying if I have gear wheels and the amount of gear wheels is smaller than the signal I get, the amount I get from signal A, which remember is 10, output a B1. I have connected the output side of the combinator to the inserter and told it that if signal B is bigger than 0, so for instance the one that it's going to output, start working. If it is not bigger than 0, stop working. Let's see that in action. I will put 100, which is enough for 50 gear wheels, but I expect it to stop at 10 or maybe 12, depending on how many iron plates are actually inputted in the assembler before the system tells it to stop. So we'll see. Here we can see there's still a B1. Now there is not. So there's 15, as you can see on the right hand side there. There are 15 gear wheels produced, which is bigger than 10. So there is no more output signal. Hence, the inserter here has stopped functioning, as indicated by the red signal, or the red light on it, I should say. The arithmetic combinator. The arithmetic combinator is slightly more complex to work with due to the nature of maths. What I mean by that is once you start multiplying, dividing, adding, and subtracting signals, things can get complicated really quickly. Similar to the decider combinator, the arithmetic combinator also has two values to work with, but unlike the decider combinator, the arithmetic combinator either multiplies, divides, adds, or subtracts value 1 with or from value 2. Then it will output a new signal with the newly calculated value. For example, if the input signal was 50 stone, like so, and I multiplied that by 2, multiply by 2, it would only take the value of the stone to make the calculation, and I could then output a different signal with a new value. For instance, iron ore. If we now look at the combinator, it has an input signal of 50 stone and an output signal of 100 iron ore. Notice how the output signal type is not tied to the input signal type, just its values. Of course, I could also take the value of two different input signals, let's say stone and wood, like so. Whoops, like so. To make my calculations. For instance, if I take the stone and subtract the wood, now these two input signals are being used, and I use it to output the amount of fishies. Now it will take the 50 stone, subtract the value 20 from the wood in this box, and it will leave you with 30 fishes. Again, notice how the output signal does not match any of the input signal types. It just uses the signal's value to calculate the result. So in this case, we inputted 50 stone and 20 wood, which we then subtracted from the stone, leaving us with a value of 30, but our output signal was set to fishes. Circuit network entities. So which entities can be part of a circuit network? Well, all entities in this row are capable of being part of a circuit network. One notable thing here is that the wooden, iron and steel chests are indeed also capable of being connected. Not all entities, however, will act the same once connected to a circuit network. A chest, for instance, can only broadcast its content across the connected wire. It cannot do anything else. The same goes for the storage tank. The pump, however, can be turned on or off based on conditions within the circuit network. For example, you might want to make sure that a small amount of oil is always available for your flamethrowers at your defensive lines. The simplest way to ensure this would be to connect the pump with a wire to a storage tank just beyond it and have the pump activate whenever the storage tank has less than X amount of oil inside it. This way, oil will be pumped into the storage tank when there is not enough, and when there is enough, the rest of the oil can continue to be used elsewhere. The inserter can also be turned on or off. However, it has another feature. The inserter is able to read the item it is holding and send this information to the circuit network. It sends the type and the amount of the item. This can be transmitted as a pulse of information sent only for one tick of the game, or it can send this information continuously. For example, if you want to limit the amount of items an inserter puts into a chest or factory, you can add a simple comparison between how much of something you want to have and how much of something there already is. On the other hand, you might want to count the amount of items that have been handled by an inserter, and then maybe using that data in a larger system. The belt is also capable of being turned on or off depending on network conditions. And like the inserter, it is able to send its content to the network either as a pulse or a constant signal, as long as the item is in that section of belt. For example, here we have a simple sorting system that can separate iron from copper. When the mixed belt comes in from this side, the copper is separated by these filter inserters and sent along the top side to the left, or the right, I'm sorry. Once they hit this transport belt, it will send a signal, a copper is here signal, to this belt, which will then stop moving. Why would it stop moving? Well, that gives these arms time to extract all the copper that is there, leaving only iron in this section of belt. Once that is done, this part will empty out. It will no longer send the copper signal to this part of the belt, and it will start working again, flushing out all the iron. Now, let me demonstrate that in real time. So I'll put in these mixed this mixed belt. So we've got iron on both sides and we've got copper on both sides. I will turn this contraption on, and now you can see we've got a mixed belt, and as long as there's copper here, this will stop moving. Only when there's no copper in this belt section will this allow the iron to go through. For those of you who'd like to know how it is exactly set, this particular belt has been set up as a read content, so it only sends out what it's actually has on it. It doesn't do anything with turning it on or off, just reading the content of the belt and sending that as a signal as long as it is actually on that part of the belt. Now the other one, that is set as an enable or disable operation. So whenever there's a signal coming in that is bigger than 1, it will disable this part of the belt. It will enable this part of the belt if the signal is smaller than 1. In other words, if it's 0. The light can only be enabled or disabled by circuit network conditions. However, you are able to give it various colors depending on the inputs given. For example, we can determine how much of a certain item is in a box by attaching a few decider combinators and lights to that box. The lights will turn on based on the signal that they are given, red or yellow or green, and the decider combinators determine how much wood must be in the box before they actually send that signal. So for instance, if there is, for the yellow signal, more than 20 wood in this box, it will send out a signal, yellow signal, at the value of 1. Let's see that in action, and then you understand what I mean. So now the box is filling up, and one by one these decider combinators will send out the signal of that color, because the box is filling up and the equations get higher and higher. Now if we take out the items, the signals will be turned off because the equations are no longer true. Hence the lights turn off. The accumulator can only send its charge level as a percentage to the network. For example, we can use that information to visualize the amount of charge we have in our system. By utilizing the charge level of the accumulator, the lights and the decider combinators, we can visualize the amount of charge that is in the system. Alternatively, we can also use that information in conjunction with the switch to turn on or off certain parts of the factory or certain parts of our power generation if we need more. And that was all I have up to that point. There were a few more things I needed to do. There were definitely a few more things that I wanted to talk about. But with the new systems being in place, that is not very useful right now. As you can see, I had a lot of stuff to talk about. I still wanted to talk about the trains. I still wanted to talk about the trash sorting system as an example of what combinators in conjunction with each other can do. And I might do that in future. But again, it'll be a while because this was a lot of work. And yeah, I hope you enjoyed the video. I thank you very much for watching. Of course, I'll be answering any questions in the comments for the next few weeks. And I will see you all in my next Let's Play.